Alright, so what we have seen is that in multivariable systems, interaction requires that the decentralized PI controllers be detuned. Usually if one of the control objectives is much more important than the other, then it is clear how the detuning must be done. You tune the control loop corresponding to the more important objective the tightest, and then take all the detuning in the other not so important control loop, right. However, there are situations where both the objectives are equally important, and then we need a systematic technique to detune both the loops systematically or equally, so that the detuning gets taken about equally in both the loops. So, how do we do that? That requires some control theory, and not some, actually a lot of control theory, and what I will try to do is go over the relevant bits, so that the systematic decentralized loop detuning procedure can be reasonably understood. Okay. So, over the next 1.5 or 2 hours, what we will do is go over the essential control theory that is necessary to understand how decentralized multivariable controllers are systematically detuned. Okay. So, let us look at seesaw systems, a seesaw single input single output feedback loop. If you look at a single input single output feedback loop, so you got your process, it has a transfer function Gp, you have a controller, it has a transfer function Gc, and you got the output is compared with its set point, negative feedback, and that is it. That is your single input single output control loop, and this is called the error, this is the control input, and of course, that is the output. So, if you look at the relationship mathematically, this block diagram mathematically, what you get is y is equal to Gp times u. However, u is equal to Gc times E, and E, the error, is equal to Gp Gc. If you can replace the error with y set point minus y, and now if you take y to the left hand side, what you will get is 1 plus Gp Gc of y is equal to Gp Gc y set point, and what this gives is y is equal to Gp Gc divided by 1 plus Gp Gc y set point, and therefore, what you get is that the servo transfer function of the output with respect to a change in the set point is actually equal to Gp Gc divided by 1 plus Gp Gc, and if you look at it carefully, if this loop was not on, if the feedback loop was not on, that means if this loop was broken, for example, let us see, if this loop was off, that is a switch there which is not connected. So, the feedback loop is off, then what you see is y, the change in y with respect to a change in y set point is actually Gc Gp, right. The numerator is the forward, is the transfer function in the forward path, and the denominator is the 1 plus whatever is there in the whole feedback path. So, what you get essentially is, so we call Gp Gc as the loop transfer function or open loop transfer function, and what we get is G open loop divided by 1 plus G open loop. Okay. So, this is the servo transfer function of the closed loop system. So, maybe we will go to the next page. So, what we have is this simple feedback control system GC GP, this thing is actually equivalent to, and this is why, a single the above block diagram is equivalent to this, it simplifies to this. Yeah, and this I will call the closed loop transfer function. All right. If I look at the closed loop transfer function, or if I look at any transfer function, closed loop, open loop, whatever. So, for example, y over y set point, any transfer function, then it will be a bunch of poles and zeros. So, okay, so let us say this is product of some bunch of zeros and a product of some bunch of, the denominator simplifies to a bunch of poles. And now let us say we say that okay, this guy is actually a step. If it is a step, then what we will have is y will be is equal to the Laplace transform of, so this is product over I, product over j, product over I, product over j, oh this is j, sorry, s minus p j times whatever is the change in y set point. So, let us say you are giving a step change in y. So, y set point is here and it changes by a unit step. Okay. Then what we have is the Laplace transform of y set point s will actually be equal to 1 by s, and you can refer to a control book to see this. And then what you will get is y actually is this guy, and ultimately if you want to get the domain time domain response y t, what you will have to do is take the separate this into partial fractions, and when you do those partial fractions, what you will get is y t is essentially equal to a over, well, a summation over j s a j over s minus p j plus maybe b over s plus a constant term, and this is assuming that all the initial conditions are 0. And so, this is y of s separated into partial fractions. Using partial fractions you can get this, and then what you will get is when you take the inverse Laplace transform, y t will actually be equal to summation a j e to the power p j t plus b, because the inverse Laplace transform of 1 over s is 1. Okay. So, therefore, you get this as the dynamic response of this closed loop system to a step change in the set point. Now, you can see that the dynamic response is is coming from these terms, and if you look at these exponentials if you plot in time, this is time, and if you plot e to the power let us say lambda t, okay, then what you will get is essentially let us see, e to the power t equal to 0 would be 1, and if lambda is positive, things will blow up. If lambda is negative, things would, this is of course 1, things would decay to 0 in long time. Yeah. So, if any of the poles of your transfer function is positive, if any of the poles is positive, what you get is you will get an e to the power that pole times t term, which will blow up in time. So, what that means is if any of the poles of the transfer function that you are looking at has a positive is in the right half plane, has a positive real part, that positive real part e to the power lambda t will blows up if real part of lambda is greater than 0. Yeah. So, what this basically gives is that stability of a system, if you have a system and with a transfer function g, this transfer function is stable if all roots of denominator, which are also referred to as poles, have negative real parts. What this means, another way of looking at it is, if any pole has positive real part, then that dynamic system, then the system is, that implies dynamic system is unstable. Now, for closed loop systems, like I showed you, the closed loop system transfer function g closed loop is actually equal to the open loop or the loop transfer function divided by 1 plus g open loop. So, closed loop system. Okay. Now, if you look at g open, okay, fine. So, what this means is, if roots of 1 plus g open loop equal to 0, if of this equation are all in left half plane, that means they have got negative real parts, then closed loop system is stable if any of the roots of this equation 1 plus g open loop equal to 0 are in the right half plane. Even if one of the roots is in the right half plane, then that closed loop system is unstable. So, if you want to figure out whether a closed loop system is stable or not, then what you need to do is figure out roots of 1 plus g open loop equal to 0. Stability is governed by the roots of this equation. This is called the closed loop characteristic equation. So, now what we want to do is figure out whether this guy has any root in the right half plane. If it has any root in the right half plane, the closed loop system is going to be unstable. So, stability or instability boils down to figuring out whether the roots of the closed loop equation are in the right half plane or not. That is the crux of the matter. How do we go about figuring it out? Well, if you have a system which has got no dead time and which is representable by rational transfer functions. So, for example, g is equal to g process may be equal to, I do not know, a second order or maybe a third order system overdamped tau 1 s plus 1 into tau 2 s plus 1 into, that is a third order lag, and let us say you got a pi controller. So, the controller transfer function is going to be k c times 1 plus 1 by tau I s. So, k c into integral time constant s plus 1 divided by, this is a pi controller transfer function. How do we get it? Refer to a textbook. Okay. So, then what you would say is 1 plus g p g c is equal to 0 is equivalent to 1 plus, well, let us see, k times k c times tau I s plus 1 divided by tau 1 s plus 1 into tau 2 s plus, hey man, let us make it a p well, okay, it does not matter, tau 2 s plus 1 into tau 3 s plus 1, and so what you will get is that your closed loop characteristic equation for this system is actually equivalent to tau 1 s plus 1 into tau 2 s plus 1 into tau 3 s plus 1 plus k times k c times tau I or divided by tau I s, that I forgot. So, there is a tau I s here, tau I s plus 1 equal to 0. Do not worry about the mathematics of it, the only point that I want to make is that as you change k c, this is a controller tuning parameter, and tau I, as you change k c and tau I, the coefficients of the s and the constant term change. If the coefficients change, then you can see that this is actually a 1, 2, 3, a fourth order system, because the highest power of s in this equation is 4. So, it has got 4 roots, and as you change the tuning parameters, the position of these roots change. So, what you will find is that if you have a feedback control system for this third order system, let us say you have fixed tau I and you are just changing k c. If you have fixed tau I and you are just changing k c, what you will find is when k c is small, all the roots of the closed loop characteristic equation are real and in the left half plane, that means real and negative. Then as you crank up the k c, you will start seeing that the oscillations are coming. What that means is, and these oscillations actually die down, these oscillations decay in time. What that means is that the roots have negative real parts, however, some of the roots are now having complex conjugate parts. These complex conjugate parts imply that you get oscillations. The fact that the real part is negative implies that these oscillations die down. If you keep cranking up the gain further, what you will find is that these oscillations die slower and slower, and there comes a gain where the oscillations become sustained. And what this is implying is that as you are changing k c, the closed loop characteristic equation roots are moving, and they are moving from the left half plane towards the right half plane, and when you have sustained oscillations, then you got purely at least 2 purely imaginary roots, and then when you crank up the gain further, the real part of the root becomes positive, and then you start getting these oscillations that blow up. Okay. So, this is what we observe in practice, and so if you have a transfer function that looks like this, you can trace the roots as k c as a function of k c, you can plot the locus of the roots as a function of k c, and this is called the root locus, and from there you can figure out, okay, at what k c does the gain, at what k c do you start getting oscillations, at what k c do you have the roots moving from the left half plane to the right half plane, and so on and so forth. So, that gives you the ultimate gain, and then of course, we have seen in the past how tuning is done. You crank up the gain, get sustained oscillation, and you say, okay, this is the limit of stability, I must run my tuner my controller at a gain that is sufficiently away from the verge of instability. So, back off the gain by a factor of 2, etc., etc., etc. All this is fine, but chemical processes are notorious in that they have got large dead times. So, a very typical transfer function would be G p is equal to first order plus dead time, k times e to the power minus dead time upon tau h plus 1. Now, if you look at this guy, the closed loop characteristic equation for a P controller, so and let us say G c is equal to k c, that means it is a P controller. If it is a P controller, the closed loop characteristic equation would be tau h plus 1 plus k times k c into e to the power minus d s is equal to 0. Now, you can see this is a transcendental equation because of the presence of this term. So, A, you do not know how many roots there are, because in a transcendental equation you cannot tell how many roots there are. If it is a polynomial equation, then the order of the polynomial tells you that okay, if the order of the polynomial is 4, there are 4 roots. So, root locus, tracing the locus of the roots is not an option here. So, for chemical systems root locus cannot be used, but the idea remains the same. As you are changing the gain, the sum of the closed loop characteristic equation roots move, and they tend to move towards the right half plane. Okay. Now, for these kinds of systems, what is more relevant is frequency domain analysis, and I will just go over what is frequency domain analysis very quickly. Frequency domain analysis, let us just say frequency domain analysis of feedback systems. Okay. So, now let us say I still have a process, and well, let us see, if you have a process, and even though that process may have dead time, let us see, let us say I have got a process with a controller, and let us say I have got a set point, same system, now of course I need a switch here which will be very useful. Okay. Now, there is something in linear systems theory that if there is a linear dynamic system, even if it has dead time, and you force it with a sinusoid, that means I have got a linear system which has got an which has got a transfer function g, and I have got an input and I have got an output. If this input is a sinusoid, then the output would also be a sinusoid. However, its amplitude may be more than the input sinusoid, and also it will have a phase lag. Okay. So, if you force a linear system with a sinusoid, after the initial transients have decayed, the linear system will settle into sinusoid oscillations, and the output sinusoid would be of the same frequency as the input sinusoid. Its amplitude may be more or less, and it will have a phase lag. So, what we are saying is, if u, for example, you are forcing a linear system with, let us say, a sinusoid that is amplitude a sin omega t, then after sufficient time has elapsed and you have allowed the initial transients to pan out, what you will get is the output would be let us see, b, a different amplitude, a sine wave with a phase lag phi, okay, as t tends to infinity. The system will settle down into these into a nice sinusoidal kind of system. Let us look at the feedback loop above, and let us say the feedback is not yet closed. So, the feedback loop is what shall we say, and by the way, this can also be represented as this guy, and I can put a multiplier by minus, well, let us see, minus 1 here. This is the same feedback system, it is just that I am multiplying by minus 1. Okay. So, let us say the input is a sine wave. So, the input is a sine wave, and let us say its amplitude is 1. Okay. If the input is a sine wave, then this would be a sine wave. If sufficient time has elapsed, this would also be a sine wave, this would also be a sine wave, and if sufficient time has elapsed, then G p is being forced by a sine wave, then y would also be a sine wave, and the signal here would also be a sine wave, right. So, what you get is, if I am forcing my set, if my set point y set point signal is moving as a sine wave, I will get a sine wave here. Its amplitude will be different and it will have a phase shift, all right. Now, let us say, and let us say this G c is just again it is a proportional controller. Now, if I start cranking up Kc, what will happen is the amplitude of the output sine wave will go up. So, this sine wave will start becoming bigger and bigger and bigger as Kc is increased. Okay. Also, the phase shift will change. If you have a linear system being forced by a sine wave, u is equal to a sine omega t, and then the output will settle as t tends to infinity into another sine wave which has the same frequency and a phase lag. And if the relationship y by u, which is a transfer function, okay, is given by a transfer function g, then what people have shown is that the amplitude magnification, which is called the amplitude ratio, which is equal to b by a, how much is the sine wave getting magnified by, okay, is actually given by g j omega, where s in the transfer function, the Laplace variable s, has been replaced by j omega, the magnitude of this complex number. Similarly, the phase lag or the phase shift is given by the angle of g j omega. And what I mean to say is, just to clarify, you see, when you replace s in the transfer function with j omega, when you put s equal to j omega, for a particular value of the frequency of the sine wave, for a particular value of omega, what you will get is that g j omega is a complex number. Now, if you look at complex numbers can have real parts and imaginary parts, and let us say the complex number is this guy, then the magnitude of that complex number is this, the length of this inclined line, and the angle of that complex number is this guy measured anti-clockwise, positive angle is anti-clockwise. Okay. This everybody knows. So, what linear system theory says is that if you are forcing a linear dynamic system with a sine wave of a certain frequency, then the output sine wave after sufficient time has elapsed would be a sine wave of the same frequency, but it will be magnified by an amplitude ratio, and that amplitude ratio is given by the absolute value of the complex number g j omega. And there will also be a phase shift phi, and that phase shift will be given by the angle of the complex number g j omega. Okay. All right. So, now why is this relevant? Well, I will tell you why it is relevant. Let us say you can see that the amplitude ratio and the phase shift are functions of omega, right, because g is a function of s. If you put s equal to j omega, the complex number, the real part and the imaginary part of that complex number will depend on omega, and as omega changes, the real part and the imaginary part of that complex number changes. As the real part and the imaginary part of that complex number changes, well, its magnitude and its angle changes. If its magnitude and angle changes, then that means the amplification of the sine wave, the factor by which this sine wave is being amplified, and its phase shift change. So, the amplitude ratio and the phase shift depend on the forcing frequency. Okay. Now, because most systems are causal in the sense that if I make a change to the input, the output takes time to manifest, to respond to the input. Therefore, these for natural systems, for most physical systems, the phase lag or the phase angle is usually negative. Okay. Also notice that if I change this scalar factor Kc, then Kc does not depend on S. Since Kc does not depend on S, well, let us see how do I explain this. Kc is a pure real number. If Kc is a pure real number, it will only affect the amplitude ratio, but not the angle. Okay. Well, you need a little bit of complex algebra to know this, but refer to a textbook. So, now let us see what I am trying to say is, let us say I start cranking up Kc. Intuitively you can see that if the frequency of the input sine wave is the same and the amplitude of the input sine wave is the same, and if I am cranking the gain up, what I will get is, I will get a sine wave which is getting magnified larger because you are multiplying it by a larger number. Okay. So, as Kc is increased, amplitude ratio will go up, the phase angle will remain the same. Yeah. As omega, the forcing frequency is changed, amplitude ratio will change and phi will also, both will change. Okay. Now, let us say I am changing the frequency, and usually the phase lag is a negative angle. I am changing the frequency of the forcing sine wave y set point, and I get that frequency at which the phase is minus 180 degrees. So, let us see, maybe I can just rub all this off because this slide remains relevant, the rest of the stuff is just okay. So, I adjust the forcing frequency omega such that the phase angle is minus 90 degree or minus 180 degrees, phase equal to minus 180 degrees. If this is a sine, so I am drawing y as a sine wave, let us see, this is the okay fine. So, y is a sine wave that goes like this. Then if the phase lag is minus 180 degrees, then well let us see. So, y would be sine omega t minus 180 degrees and some factor b, and what that means is that t equal to 0 sine minus 180. What is sine minus 180? Sine minus 180, and then when it starts to, okay. So, yeah. So, then your u is changing, this is u. If this is u and the output sine wave is lagged or has a minus 180 degree phase shift, then what you can see is that this signal y, and maybe I should draw it with a blue curve. Okay. One more thing. So, I just told you if you adjust Kc, you can get the amplitude ratio that you want. Whatever amplitude ratio you want, you can get without affecting the phase. Okay. That being the case, let us say I adjust the omega to get a phase shift of minus 180 degree, and I adjust Kc such that amplitude ratio is equal to 1. Okay. If I have done that, then if the sine wave, input sine wave looks like this, this is u, meaning that this is y set point, then y would look like mirror image of this guy, and of course, the sine waves go on, and its amplitude would be the same as the input sine wave because the amplitude ratio is 1. Kc has been adjusted to give you an amplitude ratio of 1. Yes or no? Okay. So, here comes a sine wave, there is the output sine wave, then when you multiply this y by minus 1, you will get another sine wave, and when you multiply it by 1, this blue sine wave will flip over the time axis, and then what you will get is your feedback signal, you know, the signal that is being added to y set point will actually look exactly like this. Yes or no? Okay. So, if I am at that frequency at which and I adjust the Kc such that the amplitude ratio is 1 and the phase shift is minus 180 degree, then this signal would be this red signal, this red wave would be the same as this blue this black wave. The red wave and the black wave would be the same. Yeah, they would exactly be the same. Now, what do I do? The feedback loop is not yet closed. The feedback loop is not yet closed. What I do is I shut down the sine wave, the forcing sine wave. So, this signal goes to 0. and I close this feedback loop. Okay. What would happen? Well, the forcing has gone to 0. However, there is this sine wave which keeps going back, and therefore, the system will keep on oscillating. On the other hand, if I reduce the Kc a little bit, then what will happen is this sine wave would be smaller, and what that means is if there is a sine wave forcing this guy, then the output sine wave is smaller, and when you feed that back in, smaller will become still smaller, will become still smaller, smaller, and basically if you stop forcing the system, the oscillations will become smaller and smaller and smaller, and the system will settle down. So, do you see that the frequency at which phase equal to minus 180 degrees is special, and if at this frequency the amplitude ratio is less than 1, then when you close the feedback loop, oscillations die out. If the amplitude ratio is 1, the oscillations will remain even though you are not forcing the system. Similarly, if the amplitude ratio is greater than 1, then those oscillations, even though you are not forcing the system, will tend to blow up. Yeah. So, what we are saying is that if you have the G plane, that means you are plotting G j omega, the real part and its imaginary part. Okay. This is actually called the polar plot of G j omega, and I will just show that to you. Then frequency phase shift of minus 180 degrees means that the angle is minus 180, this is the angle. Amplitude ratio 1 means you are talking about this complex number. Yeah. So, this number minus 1, real part is minus 1, imaginary part is 0, is actually special. Okay. And what we will just discuss very soon is that if for all value, if you have G j omega, if when the angle is minus 180 degrees, absolute value of G j omega is greater than 1, that means G j omega is here, then the system is going to be unstable. If it is here, it is going to be stable. If G j omega is this guy passing through minus 1 0, then it is going to be on the brink of stability and instability, right. And let me also introduce at this point in time the polar plot of G j omega, polar plot of G j omega, which is nothing but you plot the real, see G j omega is a complex number with a real part, and the real part depends on omega, plus j times b, which is the imaginary part, and the imaginary part also depends on omega. Yeah. So, the plot of the real and imaginary parts as omega goes from 0 to infinity, from low frequencies where the sine wave is really slow to very fast sine waves, that is called the polar plot or Nyquist plot of a transfer function. Okay. Now, let us say your transfer function is, let us just say, I mean, let us say your transfer function is, I do not know, first order. If you look at a transfer function that is first order, so let us say your transfer function is G is equal to, I do not know, k over tau s plus 1, then G j omega will be equal to 1 plus tau omega j, and then if you multiply by the complex conjugate of the denominator, what you will get is actually k times, well, 1 minus tau omega j divided by 1 plus tau square omega square, and of course, k is multiplying everything, and therefore, what you will get is the real part of this complex number is k by 1 plus tau square omega square, and the imaginary part is plus j into minus omega tau divided by 1 plus tau square omega square. Okay. And then you will say, okay, the magnitude of g j omega, magnitude of g j omega is going to be, oh, of course, I forgot the k here, magnitude is going to be k over square root of 1 plus tau square omega square, and the angle is going to be the angle of a complex number. If you have a complex number, what is its angle? Its angle is, well, if it has got a negative real part. So, if it has got a negative imaginary part, the angle is, okay. So, this is the complex number that we are talking about. It has got a positive real part, this is positive, and it has got a negative imaginary part. So, the complex number is in this fourth quadrant. So, the angle is going to be whatever is the magnitude of the imaginary part. Okay. So, the angle is going to be negative, and the angle is negative because you are going in the clockwise direction. Yeah. So, negative tan inverse real part by imaginary part, that is essentially going to be omega tau. And now, you can see that as omega tends to 0, the magnitude of the complex number is k, angle is 0. As omega tends to infinity, magnitude tends to 0, angle tends to minus tan inverse infinity, which is minus 90 degrees. So, if you look at the Nyquist plot of a first order transfer function, it looks like this. It starts at k, and then as omega is increased, it goes this way. Yeah. This is the Nyquist plot of a first order transfer function. Let us just take this guy only. G is equal to k over 1 plus g j omega is equal to tau omega j. Okay. Now, if you remember any complex number, for example, let us say I have got a complex number z is equal to a plus b j. This complex number can be represented as, this is the Cartesian form. It could also be represented as magnitude of z times e to the power angle of z times j, where magnitude of z is equal to square root of a square plus b square, and angle of z is equal to tan inverse b by a. I am assuming both b and a are positive. If they are not, then you will have to think which quadrant it is and then adjust the sign. Okay. How are they equivalent? Well, you just put these expressions in there, and then what you will find. So, if you have an angle, this is b and this is a, and this is the angle, then okay, okay. So, what you have is this angle is phi, let's call this angle theta or angle of z, then this guy would be square root a square plus b square times e to the power angle. So, e to the power angle of z j, and by the Euler identity, you know that is equal to square root a square plus b square times cos angle of z plus j times sin angle of z. And once you see what the cos of this angle is, the cosine of this angle is what? Cos of this angle is a by square root a square plus b square. So, that is equal to square root a square plus b square times cos of the angle is a by square root a square plus b square plus j times sin of the angle is b by the same square root term, and then what you find is that the square root term cancels out, which is equal to a plus j b. So, you see that b j. So, you see that this is actually equal to this guy. This is called the polar form representation of the same complex number a plus b j. It is much easier to work with this, and I will just show this to you for this first order transfer function. What do we do? Okay, so, this will be equal to g j omega will be equal to k divided by, so k remains k, and I can replace this complex number by magnitude of this guy, and the magnitude of the denominator is going to be square root 1 plus tau square omega square, and the angle of this guy will be e to the power imaginary part by real part, tan inverse of imaginary part by real part. So, that is going to be tan inverse tau omega, and then what will this guy turn out to be? This guy will turn out to be k over square root 1 plus tau square omega square. When I take e up, what I will get is omega j, sorry, negative tan inverse tau omega times j. Yeah. So, from this by inspection you can see that this guy is the magnitude and this guy is the angle. So, you can see that if you work in polar form, and this particularly helps us, for example, if you had G is equal to 2 lags in series, for example. So, let us say it was, I do not know, k times tau 1 s plus 1 times tau 2 s plus 1, then all you have to do is then G j omega, for example, here let us fix this, then G j omega would be k times tau 1 omega j plus 1 tau 2 omega j plus 1. This, treat this as one complex number, this is another complex number, and this is another complex number which is real. Okay. So, then the total product G j omega, and express each of the complex number in their respective polar forms, this will be e to the power 0 j. Okay. And the guy here will become, the first complex number will become, its magnitude is square root 1 plus tau 1 square omega square, its angle is e to the power tangent inverse tau 1 omega times the second complex number is 1 plus tau 2 square omega square, and its angle, oh missed the j, this is the angle, that is the j, its angle is e to the power tangent inverse tau 2 omega times j. And then when you say okay, therefore, G j omega is equal to, oh forgot the k, is equal to k divided by square root of 1 plus tau 1 square omega square times square root of 1 plus tau 2 square omega square times e to the power, and now you can see negative tangent inverse tau 1 omega plus tangent inverse tau 2 omega times j. So, you can see you easily get the magnitude and you easily get the angle. The same thing if you were to do with, you know, let us say you wanted to do the same thing in Cartesian, then you would have to multiply by complex conjugate of this guy, complex conjugate of this guy, complex conjugate of this guy, and let us say you had not just 2 lags, maybe 3-4 lags, then the multiplication and all the algebra will get very messy. On the other hand, if you deal with a polar system, then what you have is that the magnitude becomes simply the multiplication of the multiplication or division of the complex number, and the angle becomes the sum of the angles of the respective complex numbers. If the complex number is in the numerator, the angles get added. If the complex numbers are in the denominator, the angle becomes negative. That is all, right. So, it is much easier to work with what shall we say, to work in the polar form. Okay. Okay. So, what would be the Nyquist plot of this guy? The Nyquist plot of this guy would look like this. At omega equal to 0, the magnitude, which is this term, if you put omega equal to 0, is actually k, this is k, angle is 0 because tan inverse 0. And then what about the angle? As the angle goes, omega goes very large, the magnitude goes to 0. What about the angle? Well, tan inverse omega tau 1 as omega goes to a large value goes to 90 degrees, tan inverse infinity is 90 degrees, this guy also goes to 90 degrees. So, 90 plus 90 is 180 degrees and the minus sign. Yeah. So, the angle at very large frequencies is minus 180 degrees, and if you basically look at what the Nyquist plot look like, or what the polar plot of g j omega, which is this guy, what the polar plot of this guy looks like, it actually looks something like this. If you had 3 lags in series, what you would probably get is something that looks like, I do not know, the angle will become minus 270. If you had 4 lags in series with all real parts, and if you do the algebra, and I am not showing it, if you had a second order denominator, but the roots were complex conjugates, then what you will get is you will get something like roots are large complex conjugate, you will get something like this, no, starting at k, and so on and so forth. So, plotting the Nyquist plot, once you start dealing in polar coordinates, is actually very intuitive. Okay. Let us look at a pure dead time. So, g is equal to e to the power minus d s, then g j omega replacing s by j omega will be e to the power minus d omega j, right. What is the magnitude of this guy? Well, the magnitude of this guy is 1 all the time. What is the angle? Well, the angle is minus d omega, and as omega increases, the angle becomes more and more negative. So, what you get is magnitude is 1. So, this is the unit circle, this is 1, this is minus 1, this is minus 1, this is plus 1. So, this is the unit circle, and the angle keeps going more and more negative. So, the Nyquist plot looks like this, you just keep going round and round in circles. It is a circle, of course, my drawing is not so good, forgive me for that. Okay. Now, let us say you got g is equal to first order plus dead time. What would the Nyquist plot look like? Well, the lag will force the magnitude to 0 as omega goes large. The dead time will cause the angle to keep decreasing, keep becoming negative, negative, negative and more negative. So, what you have is you are going round and round, but the magnitude is becoming smaller and smaller, and ultimately at large frequencies. This is what the Nyquist plot for a first order plus dead time would look like, and of course, the direction is as follows. Yeah. So, you can see that if you have the transfer function replace s by j omega, the Nyquist plot is a piece of cake. And then what we are saying is, if you look at the open loop system, please remember what did we do here? Yeah, yes. When we were looking at the amplitude ratio and the phase shift, this guy was not closed. Yeah, this guy was not closed. Because this guy was not closed, what we are doing is we are looking at the and the amplitude ratio, like I told you, is well, where did I tell you that? Let us see. Well, that is okay. And the amplitude ratio is given by AR is equal to, at some frequency omega is magnitude of g j omega, that relates the transfer function, and phi is equal to angle of g j omega at that frequency. Yeah, this is what I had told you, but please note, since the feedback loop is not closed, G in this case is nothing but GC GP, and I am looking things out here. Yeah. So, I am looking at this guy, and so what was I trying to say? I was trying to say, okay, you are plotting g j omega as a function of omega, and so what this is saying is, if you are plotting g j omega as a function of omega, the amplitude ratio of the open loop system without the feedback loop closed, if that plot looks like this, let us say, or that plot you cranked up the gain. So, that plot looks like this, or that plot looks like this, you are cranking up the gain. So, the Nyquist plot is moving out, okay. Kc is being cranked up. This guy corresponds to when the angle is minus 80, the amplitude ratio is less than 1. This second curve, this is the first curve, second curve, third curve. First curve, when the angle is minus 180 degrees, the amplitude ratio is, what is the amplitude ratio? For the first curve, the amplitude ratio is less than 1. For the second curve, when the angle is minus 180 degrees of g j omega, the amplitude ratio is exactly equal to 1. And for the third curve, which is this guy, the outer curve, when the angle is minus 180 degrees, the amplitude ratio, this point is minus 10. The amplitude ratio is greater than 1. So, you can clearly see that if I am plotting the Nyquist plot or the polar plot of the open loop system transfer function, then if at the frequency of minus 180 degrees, the amplitude ratio is less than 1, equal to 1, greater than 1. So, this guy would be stable, this guy would be sustained oscillations. So, it is at the verge of instability, and this guy would be oscillations that blow up. So, it is unstable, oscillations that blow up. So, it is essentially unstable and oscillatory. Yeah.